Steve Oberlin, Vice President and Chief Technology Officer, NVIDIA. Accelerating understanding, machine learning, intelligent applications, and GPUs.
I have a lot of clicks planned, so I'm a little worried about the technology holding together. Yeah, there's actually more text supposed to be on that slide as well. So I'm going to spend a little time talking about high-performance computing and a revolution that is occurring that I think is going to, and in fact already is, affecting everyone's life. I've worked in high-performance computing all my life, and it has really dramatic changes that have been fostered on science and materials, and improving the efficiency of transportation, and including improving biology and even predicting the weather. But if you think about how high-performance computing has influenced people's lives, it's been somewhat indirect. We benefit by having more efficient transportation or whatever, but very few people actually get to touch high-performance computers directly. This is changing, and starting at the opposite end of this scale, I think a good place to start is to talk about smartphones. In 2007, Apple introduced the iPhone, and initially, Steve Jobs was very reluctant to make the developers allow them to have access to the developer capability to write native applications for the phone. Apple provided a certain small number of utility applications, but essentially, Steve Jobs' vision was that most applications were going to just be web applications, and you would have web jumpers on home screens, and that would take you to an application hosted on a data center somewhere over the internet. But eventually he relented, and application developers jumped on the platform, developed hundreds of thousands of apps. And we heard terms like, there's an app for that. And it's like, almost any particular service or web page you go to, they want you to download their specialized app for that particular service. The amazing thing is that really the interface was so natural that even, my mother, for instance, could install an application on what is actually a computer. Pretty amazing. We filled our phones up with this stuff. But eventually, what we came to realize is that there's a few applications that are actually portals to data center hosted applications that actually are providing immensely valuable general services to us. They're places for us to connect with our families, with our friends. They're ways for us to manage our data, our photos, to upload information, to share. There are ways for us to distribute news, et cetera, in a curated fashion really rapidly. And this has become an entree, if you will, into a new kind of codependency that we have with our technologies. Our societies are very dependent on technology already, but now we're starting to have a personal relationship with these data center hosted applications. And those data centers themselves are immense. And the applications that they're running are based on huge algorithms and tremendous computing capability being applied. So the interesting part of this for me is that our data is really the basis of the service that these large internet-based service providers are providing to us. And there's a virtuous cycle here because we're the sensors providing an incredible amount of information, both directly, the things we upload, but also indirectly about that can be collected just based on their observations of our taste and their analysis of the data that we upload. And in return, we gain a lot of benefit from this. They customize services, do recommendations, et cetera, and improve our lives in a lot of different ways. We have this symbiotic relationship, and we're essentially becoming part of a cybernetic organism in a way. Now, there's a lot of reasons to be concerned about that, but the bottom line is we've created really an immense amount of data, and we're continuing to do that. There's over 3 exabytes of data, and again, missing text here, but in the World Wide Web, and Walmart collects over 2.5 petabytes of data per day from their transactions. Facebook, over 350 million photos are uploaded every day to Facebook. And YouTube, over 400 hours of data are uploaded every minute. So good luck keeping up with that if you're going to try and watch it. So the big question is, how can you organize this data? It's not organized in classical databases with lots of metadata. In fact, often the data itself isn't tagged or tagged reliably. Nonetheless, there's a lot of tagged image data out there, for instance, but let's say you want to find pictures. You can search images, man texting, and you'll find all the photos that had been tagged that way, and the same, obviously, for the opposite gender. But if you do something a little bit weird, you might find that not only are the tags failing, but they're unreliable as well. People upload a picture of their car and then put a caption on it saying, "My baby," right? And so if you're searching for babies, who knows what you're going to find. This is what we would really like. What we would really like is for computers to be able to understand the content that we're uploading. And so one good example here to describe a really huge success story is Imagenet. So maybe 6 or 7 years ago, Imagenet basically paid a lot of people using Amazon Mechanical Turk just a few cents each to go through a huge database, many millions of photographs, and label everything in the picture. And they gave these pictures out and collected the data set, and they created a competition where they made available this data set to companies to train or develop image recognition algorithms. And then they had a set of images that was the test case, and they scored entrance on that. And for decades, really, people have been working on hand-coded feature detectors and recognizers and classifiers, et cetera, and advancing the state-of-the-art, 1% or 2% per year. But an amazing thing happened in 2012 when suddenly there was a huge jump in capability. And this was due to a group from the University of Toronto applying deep neural networks. And suddenly the rate of recognition accuracy improvements accelerated. And not coincidentally, there was a huge shift in adoption of both the technologies underlying the computation to GPUs for reasons I'll explain later, but also all of the teams essentially abandoned all of the hand-coded feature detectors and classifiers that they had been working, some of them for their entire careers to develop. And the result is startling. Today, actually, there's a race going on between large companies who've been publishing improved results, and they've now reached a point where they have now superhuman capability to recognize and classify. The accuracy rate is actually better than a trained person. So the technology that they're using is deep neural networks. Now, deep neural networks have a hierarchical organization. Pictures go in one side. And then there's several layers of classifiers that look at images and try to detect edges, that then assemble those edges into kind of sub-pictures, if you will. And then assemble those sub-pictures into things that can ultimately be output as recognized signals saying it's a face, or it's a car, or it's an elephant, or a chair. And the really interesting thing is the way this seems to resemble how neurologists believe our own retina and the pipeline on the way to the optic nerve works, that there are simple tasks that are being done to detect edges, et cetera, and then a hierarchical organization to the recognition and assembly of the higher level concept that this collection of pixels represents. So a little more on deep learning. Deep learning is biologically inspired, but it's not biomimicry. Biologically inspired is like, designing an airplane from observing birds, but then actually doing the science and figuring out how lift works. There's another side to this, and it's called neuromorphic computing. And this is actually taking neurology learning around how neurons actually are observed to work and trying to replicate that in hardware. And that's really promising. It has a lot of potential advantages, but the truth is it's not really ready for prime time, and that's not what I'm talking about. So let me move on here. So a brief history of neural networks. Neural networks have been around since the 50s, really. The perceptron, and there were a couple of similar things invented in the mid-1950s. And there was a big hype cycle. Everyone thought, wow, this is really cool. You can train this neuron to represent and classify things. But unfortunately, it was proved to be really limited to just simple linear classification cases, and thus began what is described in the neural network research world as the first nuclear winter, because there were several decades where it was really impossible to do research, get funding, publish papers, because everyone said, wasn't it proved that actually, those are too limited for reasonable applicability. Then in the 1980s, an algorithm called backpropagation was actually simultaneously discovered by a couple of different researchers. And they discovered that if you connect some additional neurons in hidden layers, that you could still train those using this backpropagation of error back through the network and follow a gradient descent algorithm, minimizing your error over many, many repetitions. And you could actually apply it to significant problems that the single perceptron was proven to be a failure at. There was a significant hype cycle. People were even building special purpose hardware. And then it was mostly proved that really conventional techniques, more deterministic techniques, outperformed these simple neural networks. And there was really only very limited commercialization of it. And so thus began the second nuclear winter from the mid-'80s to actually just a few years ago, 2012. So. And in fact, if you talk to researchers in the neural network world today, one of the things they're most afraid of is that the current hype cycle around deep learning, they're worried that there's going to be a discovery of limitations that is going to crush hopes and expectations, and there's going to be yet another neural network nuclear winter. So what's different now? Is it really different? Well, I think, yes, it is. So there's really three things that researchers talk about. I think there's actually a fourth that is driving things forward with a lot of energy and makes a nuclear winter, a third nuclear winter, extremely unlikely. The first of these factors is data. We have a lot of data. We have huge amounts of data that is being uploaded to all of these sharing sites. We're generating all of this data. We also have way bigger models. Instead of 3 layers, one hidden layer. Recently, just a few weeks ago, I saw Microsoft research working with networks that have 1,000 layers and billions of parameters. This is becoming very common, and the growth rate of the model size is phenomenal, about an order of magnitude per year. And we also have, and it's required, we need way more powerful computers. And fortuitously, and this is purely by luck, NVIDIA did not plan this, GPUs happen to be really good at doing the kind of matrix calculations that support and underlie most of the neural network algorithms. So there is a fourth factor, and that fourth factor is these hyperscale, internet service, internet-based companies' business models, because they're delivering these services directly to our phones and sometimes to desktops and tablets and the like, they're able to almost instantly, every time they get a slight advantage in the efficiency, an improvement in the efficiency of ad placement or of recommendations that they're making, or they can do a slightly better job understanding your speech, they can instantly deploy that to all of us. And so if you've really been paying attention, the speech recognition of your phone has been getting amazing. It's really good. Noise rejection, I yell at my phone when I'm driving down the highway with my windows open and the car, is not a new car, so it's already loud. And Google gets it perfect. It's really amazing. And it's that monetization, that instant monetization, that is really driving this from a financial standpoint. So just a few quick examples. Baidu is the Google of China. Actually, they say Google is the Baidu of the US. They have a great visual search. You can take a picture with your smartphone, upload it, and instantly find out. It'll give you, hundreds of people who look a lot like you. Or you can, find a lot of pets that look like your pet. You can upload all your photos and find and sort them this way. They have shopping apps that you can take a picture of someone wearing a garment, and it will find that garment in a catalog for you, so you can buy it if you want. You can say, I want pictures that look kind of like this, and it'll spit those out. And they're also working really a lot in the speech arena. The speech uses time series data, and so one of the things that's really important for that is kind of a recursive network. They've been able to take data sets, because one of the big challenges is getting labeled data sets that you can use to train these networks. They've done some really clever work to synthetically multiply the size of the data set by distorting it, adding noise, things like that. And they've achieved some remarkable results, parallelizing their training algorithms, and they've been able to then achieve some really dramatic results, actually to the point where today, and here we go. Today, they're actually, again, achieving superhuman results. Their error rate now on speech recognition is better than human beings. And they use the same network on English and Mandarin. So obviously, Google making huge use. This is the number of applications that are employing internally at Google. And all these things are delivered to us basically over the internet. It's now over 2,000. For instance, they look at their street view information and look not only to confirm building numbers, but they also try to decode and understand the signs. They tag photos that are uploaded with captions. Sometimes there's some errors. That is not a man flying through the air with on a snowboard, for instance. They're also now using something called reinforcement learning, which was pioneered by Google's DeepMind acquisition from the UK. They're training neural networks to play Atari and to play Go. Recently bested the best UK player 5-0 and a Korean master, Korean master 4-1. In something, playing at a level that people thought was going to be 10 to 100 years into the future. So this is very real technology. It's being applied in autonomous vehicles, recognizing signs, detecting and outlining pedestrians, et cetera. NVIDIA even has a car that they have trained with end-to-end neural networks, but essentially just by driving, it has learned to drive. So these are all the signs that, not of the apocalypse, but that the AI race is on, right? This is being driven by competing companies. There's an economic model here. This is something that is mostly invisibly being pushed out to everyone and improving their life. So why GPUs? In just a few seconds. Google initially did a big unsupervised training process or project. It took 16,000 cores, 3 days to train. Essentially, the same thing was done on 3 GPU servers for just a tiny fraction of the price. And that's just an example of the huge savings. And that's really important because right now, deep learning progress is limited by availability of people who know what they're doing, and so giving them better tools means you can apply it across a much wider space. I'm going to finish in 1 second this bit.
Thank you.